Mm-mm. Hello, everybody. Sorry, chat is inside. Just give me 1 second. Hi, everybody. Are you able to hear me? Can you guys say how audio is? So this is actually feeling kind of awkward sitting here in front of the camera and talking live to you guys. But I thought that I will try this out today. And I am planning to do a live stream tonight and assemble a laser engraver. But before I am going to do that, I need to try out if Technic is working. And so I thought, well, maybe let's take half an hour, try out if everything works, and then I'm not so stressed out for tonight. Okay, no delay for you? Hi everybody. Yeah, let's start. Perfect, thanks. So, let me try this out. You really need to be... So I'm doing this the first time today, so just relax if everything is not working out as it should be. I hope you can hear me. I hope the cameras are working. So in order to, well, not sit around and just talk, I thought we, well, do some tests. I will show you what we are going to be doing. All right, so let's see. Let's see if the cameras are working. So this is the big camera where you can see me all the way. Then I have my small camera. Perfect. This I think is also working. Let's get back to the big one. And now the stream is stuck again. Damn it. Wait a second. I think we're good again. "10 seconds delay between audio and video, or just 10 seconds delay in the chat?" Okay, so let's see if the overhead camera is working. Yeah, that's also good. You can see the specimens I would like to test with you, but we are getting to that in a second. Perfect. I'm happy that audio and video are working and that you are also able to hear me. Okay, so this is my desktop. I think you're also able to see what I'm seeing right now. And so I guess we're gonna start. Let's see. Alles perfect. All right, guys. So what we are going to do today is the following. As you might have already seen in the thumbnail, I have these pretty hooks right here. There has been a blog post quite a while ago from a company called, I think, Wolfcraft, who were printing some of similar hooks out of different materials like ABS, PLA, polycarbonate, nylon, and stuff like that. And they attached a big weight to that, lifted it up with a forklift, and then, checked out at which point they were breaking. I think that was a pretty nice idea what they had, but the approach is not as scientific as I would have liked it to be. So since some of you, well, maybe some of you are knowing it, but I have this pretty 3D, this pretty tensile testing machine, which I am using to, get my material data for the material tests I'm doing. And I'm not only to put, tensile test specimens in it, like the ones, just give me a second. I don't find any of these at the moment, but they just look like dog bones. Well, we're not going to test those. We are using my tensile testing machine, and we will try to see how much load these, come on, focus, how much load these 3D printed hooks can take. And maybe there is something interesting about these. So I have them out of 2 different materials. I have 3 of them which were printed in ABS. So this hook right here was printed in ABS, just lying on the build platform and this way. Then I have 1 hook which, come on, focus. Focus. Yeah. There we go. So this one was printed standing. So when we test this one, we will see how the layer adhesion is in the part. And this should give us a good idea how strong the material itself is. And then there's also something interesting. So as you guys know, ABS can be smoothed with acetone vapor. And this hook right here, which was also printed in the line position, was smoothed with acetone. So we get this nice finish right here in the outset. And I want to know how the impact on the strength of this hook is if you smooth the hook with acetone. And then I have 2 other interesting hooks. These are hooks which were printed in Ultimaker's nylon, and these are not the first tests which I did. I actually already tested quite a lot of these, but the nylon from Ultimaker, I just wasn't able to get it to fail because the material was yielding, but it just did not break. And I optimized the design a little bit, and I am quite interested to see if we are able to break them now or if they will just yield. So all right, let's probably dive right into it. Let's get back to the other camera. Yeah, perfect. So tensor testing machine. So it's actually pretty simple. So it consists out of these two elements, which can be used to clamp my parts. I currently have these U-shaped 3D printed hooks in there, which I'm using to just well, fix the hook in the fixture. Then we have right here a force transducer. This force transducer is well, giving us a reading about the force which is currently applied on the specimens. And then I just have two lead screws right here on the side and stepper motors with gears up here, which are controlled by an Arduino board in the back, and they're turning. The upper part is, well, moving upwards, and at some point our specimens will break. Yeah, it really looks shiny. So I didn't really vapor smooth that many parts so far, but well, one reason for that is that I usually don't print with ABS because either I am sucking at printing ABS or just ABS sucks because I usually don't have good experience when printing ABS. But I have some ABS from which ABS was I using? Well, I don't remember, but that's a blend of ABS which is not really that prone to warping due to a special formula, and that prints actually way better than the standard material that you usually get, or yeah, the standard ABS. All right, so give me 1 second. How are we? 66 persons. Yeah, that's really awkward. Yeah, I haven't been in front of the camera quite a lot so far, so it's still something really new for me. So, well, let's dive right in. Okay, so we will be starting with our first ABS part. Wait a second. Let's change the camera. Yeah, so I think this thing is working. Yeah, so wait a second. So I have a small remote right here in the front where I can, well, move the clamps upwards and downwards in order to get the right distance between the fixtures, that the part is not under load when I start the test, and then it gets loaded as soon as I input the right command. So what we're gonna be doing, I will start the Arduino client right here. Serial monitor. 1 second. Yep. Are you guys able to see this right here? I guess you are. So let's start with the first specimen. So what we're gonna do is, damn it, this is really new to me. So I'm going to take the specimen, take the two U-shaped clamps, put everything inside. Let's see, fix it. Okay. So the other side. Let's maybe change the camera. Where are we? Yeah, there we go. Okay, so what you are seeing right here on this side is the force in newtons, which is currently measured with the load cell, which I have in here. And this should be 0 in the beginning, because otherwise I will get false readings. Okay. All right, so that's in. Okay, so that's kind of loose, and we can see in the Arduino monitor that the force is more or less 0. So I will be starting the test. So let's just put M14 in there. M14. Yeah, I should have probably tried that before. M14. Yeah, there we go. Okay. I think it's kind of similar to Titan X. Yeah, you are right with this. All right, so we have the first test specimen destroyed, and it actually failed at around 400 newtons. So that's around 40 kilos. So that's 80 pounds for the first hook. I will just put this now in my table. Wait a second. Okay, put it in here. And then we will see if vapor smoothing is actually changing the strength of the material. Okay, so first one is done. Sorry guys, if you're wearing headphones, this might not be the nicest sound which is coming from that stepper motors. But yeah, okay. First one's out. Let's take a look at the hook. So come on. There we go. So we see where it failed, and you can nicely see the white lines right here, which start to form at the point when the material is starting to yield. If I break this open all the way, you can see how it looks from the inside. So I didn't print these specimens like with 100% infill. That's actually not what I want to have, because this shall be a good representation of the settings you usually use if you print a part. So this has, I think, a wall thickness of 1.3 millimeters. So that's 3 perimeters with a 0.4 millimeter nozzle, and just 20% infill. But for such a part, the infill is not really actually doing anything. It's just there for that it prints nicely. Let's put it that way. Okay, let's see what's going on in chat. Yeah, Jay, you are right. PETG is really very brittle if you load it quickly, but as soon as, well, if you're only loading it very slowly, you will also get lots of yielding and not the brittle fracture you usually see from PETG parts. But for this reason, I also have an impact testing machine, which I also might be showing you in the future. All right. So let's continue with the vapor smooth part. So just as before, I put it in there. Let's put it right here in the fixture. Okay, that's fine. Then we will get this side down. Damn it. Sorry guys, I'm still a little bit nervous since, yes, I said, I'm not really used to standing in front of the camera that much, so please excuse that. Wait a second. So this is the vapor smoothed ABS part. Okay. Other side. Okay, let's switch to the, sorry guys. Dang it. Okay, let's get back into here. Okay, I really need to follow chat a little bit more. That's Mikulash, yes, I have been printing the tensor testing machine on, well, sorry, I have been building the tensor testing machine on my own. This has been a project which I had been doing kind of actually more or less a year ago. And yeah, this was a really fun project because it involved CAD, it involved playing around with load cells and strain gauges and Arduino and stuff like that. So that was pretty cool. I will be releasing the plans sometime. I have them lying around somewhere, but before I want to release it, I really want to, well, get everything nicely done. Sorry, I'm just not used to that at the moment. Wait a second. Yeah, there we go. So let's get back to the 0 position where we can start the test. So, okay, now we have around 0 newtons on our specimen. So this is our starting position. I put M14 right here in the command prompt and we're gonna start. We're at 380 newtons, 385, and now we have a break. Okay. All right, so we failed at 385 newtons. So that's 5% less than the other specimens we have tested, or the other specimen which we have tested before. So it's in the same ballpark. Give me 1 second. I really need to hook up a second monitor because this is just way too much fiddling around. let's see, we will need this screen right here. Okay, so right here we have the Excel table where I have put in all of the results. I will just create a line plot and then we can see how the two hooks behaved, and it's actually, well, quite similar, but the one which has not been vapor smoothed, so the blue line right here, this one seemed to have started yielding way later, so in this region, whereas the other hook already started yielding right here. It yielded way longer until it broke back here. And this is something which I already noticed when I did my tests earlier. So I did some tests right after I performed the vapor smoothing. Wait a second. So there we go. I did some tests right after I did the vapor smoothing, and I noticed that the parts were way softer than they used to be before. So I thought maybe there is still some acetone in the part, so the part is still soft. So some of the surface is still like in, well, a little bit solved. This specimen, which we have just tested, was laying in my office for like 1.5 weeks, and it already got better, but it's still, I think, not at the same level as just a directly 3D printed part or 3D printed ABS part. All right, let's take a look at chat again. Yeah, Jay, sorry. I'm just a little nervous. You really have to give me that. Jojo, yeah. I'm getting along better with ABS since I'm also using a enclosure for my Mark II, but when I use the enclosure, it's usually in the basement and always carrying my printer down the basement, printing some parts and getting it back up right here into the office. It's just a lot of hassle, and it smells, and PLA prints better, so I usually try to, well, walk around ABS as much as possible. The number on the X graph, that's actually just the data point which has been collected. So this is not 100% a stress strain plot, because as I have it right here, I don't have an extensometer which measures the strain in the part yet. I usually use my camera for that, and I can then add these values in post-processing. But for testing parts live, that's just not possible with the setup that I have. Okay, let's get this part out. And take a look at the fracture. Let's change the camera. Damn it, focus. Okay, so the fracture still looks kind of similar, but it's actually not between the layers. So this might actually be an indication that the layers fuse together a little better when using vapor smoothing. But still, it seems that the part is still kind of a little bit softer. I don't know if that would get better if I would just, well, put it somewhere for a longer period of time, or put it in an oven that it can evaporate, or the acetone can evaporate. Yeah, but well, if you guys are interested, I might really take a look in that and see how the real influence of vapor smoothing is on a 3D printed part, on the strength of a 3D printed part. Ugh. There's still some. Wait a second. Yeah. Let's take a look on the inside again. Oh, I love my macro lens. So yeah, that's how it looks from the inside. Alrighty. Okay, so the next specimen we're gonna test is this one right here, which has also printed with the same brand of ABS. Ah, now I remember. Sorry. The ABS is actually from Spoolworks, so that's the normal Spoolworks black ABS which I had been using. And this ABS seems to print pretty nicely and not with the amount of warping you have with a normal regular PLA. Sorry, let's get back to the chat. Which procedure did I use for vapor smoothing? So I just, sorry, let's get the camera back. So I used just a big jar, put some napkins on the inside, and then just poured a bunch of acetone on the inside, put a lid on it, put the part on the inside hanging from like a little piece of wire, putting it on the print bed of my CR10, getting that up to like 50 degrees Celsius, and then just leaving it in there for around like an hour. You really need to take a look at it and well, get it out as soon as you are happy with the result. Other questions? There is no substitute for empirical testing. Yeah, you're right. Okay, so let's take a look how the part which was printed this way fares in comparison to the other one. So how the layer adhesion is. And if I remember correctly, I actually printed this part in an enclosure, so at around like 40 to 50 degrees Celsius ambient in the box. Focus. Okay, first side is in. We will get this down. Okay, this is fine. Okay, so we can see that the part is still dangling around a little bit. So there, it's not loaded yet. I will, give me 1 second. So let's see, let's get this back up. So now we are at 0, and let's start the test. Maybe I move the camera a little closer to the specimen that we might be able to see the failure better, which I'm quite sure will happen much earlier than with the last one, because this is kind of just testing the layer adhesion of the part. Wait a second. All right, so we are at 0, and let's start the test. Okay, 10, 20, 30, 40, 50, 60, 70, 80, 100, 130, and we are done. Okay, so as you can see right here, we have failed at around 135 newtons, so that's 13 kilos, like, well, 25 pounds, which is way less. That's actually a factor of 3 less than with the other specimens. Let's take the values and put them into the table. Just copy and okay guys, that you can also see what I'm doing. Yeah, so I copied the values and I will be putting them in here in my table. Okay, so you see how the, well, wait a second, let's put a little bit more data in here. 40, so there we go. Okay, so at first the stress strain curve had kind of the same slope as the other specimens, but then something happened, probably on the inside. Something was not working perfectly, and then just it suddenly failed at this point right here. And if you just take a look at the magnitude, this is at 130 newtons, and this is 400 newtons. So we have a factor of 3 in between. Okay, so what have we seen with the ABS specimens? So ABS seems to be kind of strong if you print it lying, but the layer adhesion, at least for the print settings that I had been using, is not the best, because the part failed much earlier, and also without any real straining, as you can see it right here. Wait a second. No, focus. Okay, so there are just really some small white parts right here where the material is strained, but you can see that the part just more or less sheared off directly in the plane where the part was printed. And this means that the layers did not adhere to each other that well, that that this kind of failure didn't happen. But this really depends on your print settings. This depends on the material you're using. I had been using Prusa's PLA, and if you print that at 240 or 250 degrees Fahrenheit Celsius, the strength of the parts, the layer adhesion is really good. So you get 70–80% of the strength as with a specimen which is lying down, and that's pretty cool. And this machine that I have just enables me to try out my print settings and see how they perform with the real strength of my parts. Speaking of this, I finally have a Patreon account, and if you pledge, I think it's $15 a month, you can send me specimens and I will be testing them for you and send you a report. So if you guys are interested in really knowing how your material performs, go take a look at the video's description and check out my Patreon page. And if you pledge that kind of money, I will be testing your materials for you. It is some kind of an effort for me, so I cannot just do that for free to everybody. But if you say you support me via Patreon and you give me this $15, I think, a month, I will be doing that for you. Okay, last material that I have. Maybe let's take a look in the chat again. Are there any more questions? The layer height that I used, I think 0.16 millimeters as a layer height. Wait a second. Okay, so this right here. Hello. This right here was printed with Ultimaker's PLA on an Ultimaker 3, and this is a really tough material. So you will be seeing that as soon as we start the tensile test. So let's get it in here. Like this and like that. Fix it. Sorry, but now I think you're able to see it a little bit better what I am doing. So I just clamp it on the upper side. I move everything down a little bit. See, there we go. Wrong direction. Close everything, Yeah, the infill was just 20%. So the 20% infill should not really add that much to the strength of the part. I did not want to print them with 100% infill. I do this with my standard tensile test specimens, but these value you're getting from there are just really hard to apply. And I wanted to get away. I wanted to find a way how I can really compare two different materials and how the amount of flex, the amount of yielding a material can do affects the real strength of the part. So as I said in the beginning, from Wolf 3D, they were testing material strength with hooks which looked kind of similar. They did not do it as scientific as with a tensile testing machine. So I more or less adapted this method and do these tests on my tensile testing machine. So we should get much more comparable values in the end. Okay, so we have our part in here. Let's switch the camera again. So again, this is now Ultimaker nylon printed on an Ultimaker 3. And you will soon be seeing how it behaves differently like all of the other materials or all of the other specimens we have tested before. Let's start the test again. M14 and let's go. So we are at 200 newtons, 250, 300, 350, 400, 450, 500 newtons, 520, 525, and now you can see the part is just flexing and yielding, but it does not really break. And we will see we are still at 560 newtons, but the part did not fail so far. It flexes a little bit, and hopefully we'll really get a failure with this part. Otherwise, yeah, we just can take the maximum value. Not really the value where it was destroyed in the end, but I think we see something happening right here. So still at 450 newtons, so that's 45 kilograms. It's yielding and yielding and yielding, but no failure yet. No, it doesn't want to give. Still going, still going. Yeah, I think we can get it to fail. I think it will just pop out of the fixture in a second. Or, yeah, no, it's failing, yay. But it took quite a lot of effort to get it to fail. Now it's ripping. You see the crack starting right here. And now it's just ripping apart. Nice, perfect. So let's stop this, that you don't have to hear this nasty sound anymore. Maybe get a little bit further back. So this is actually what happened. So we did not really break it in half as the other ones, but we got it to fail in the end. Let's just release the stress a little bit. There we go. And it doesn't really get back to its original shapes. So it was really at the point of failure. I am actually quite impressed about the Ultimaker nylon because, well, I used to work just a little bit with nylon so far, but I always had the problem that they are really prone to moisture, and this brand of nylon is really nicely usable. So we have been using this for quite a while in no enclosure, and it still prints pretty nicely. Okay, put the camera back. There we go. I will now just copy and paste the values into my Excel spreadsheet in order to see how this material actually did and how it compares to the other materials we have tested before. Copy and then paste it in here. Okay, so I have to increase the range a little bit. Yep, this way. Okay, so what we can see, so it was able to bear way more load than our ABS. Sorry, can you damn it. I need to change the screen before. I think there we go. So I think you should now be able to see the graph. I make it a little bit bigger that you are able to see everything. So these two lines were our ABS. This one was the ABS, which was printed, well, straight upwards in Z direction. The nylon was doing really well and up to this point. So we have like 20-25% more load which the hook was able to bear, and then it started yielding, and at these points right here you can see where the crack started up till the end where it really failed, and then I stopped the test. Okay, let's get back to our come on, there we go. All right, so are there any more questions in chat? No. Yeah, it was Ultimaker nylon. So I think it's 60 bucks a roll of 750 grams of material. It prints really nicely. So this kind of closed ecosystem of Ultimaker, the materials are more expensive, but it just works. I do have to give them that. And especially if you are a real company and you don't do 3D printing just as a hobby, it is sometimes cheaper for you to just pay a little bit more for the material which Ultimaker is selling, but in the end just save on time, and that also saves you money. So yeah, enough for that. I'm very happy that all of you guys joined the live stream, the test live stream. I will be starting a new live stream where we will be assembling a laser engraver tonight at, I think, 6 p.m. That's 3 hours from now, so I still have some time to relax a little bit. Tonight, Robin Reiter is helping me out a little bit with techniques and everything. I think I have already learned a little bit. I'm not as nervous anymore as I was in the beginning. Thank you guys for joining me, and maybe hopefully I see you guys tonight again. So have a good one, and until next time, or as I used to say it, auf Wiedersehen.